Okay, so next we're going to talk about waxes. Waxes are very similar to the structure of fatty acids. So they don't have the COOH. They actually have just a long ester chain on both sides. And no, you don't have to name these. But basically what this does is it produces a large amount of non-polar strands that can be broken down in the body a little bit more. But these are non-polar ways or hydrophobic coatings found in nature, such as beeswax and earwax and all that yummy stuff, okay? Okay, so triacylglycerols or triglycerides, you've probably heard of either of those. They react in order to actually store your fat. And what you have here is we have 3 fatty acid chains. I just showed you different stuff just to be different, okay? And this molecule right here has 1, 2, 3 carbons, and it has an OH group on each. Now be aware of the fact that that probably doesn't really look like this. It looks like that in many texts because it looks pretty. But if you ever see it like this, or something similar, that's still the same molecule, right? We have something like that. So you've got 1, 2, 3 carbons in a row with OH groups on each of them, okay? And what it's doing is it's combining with these fatty acid tails, and together this makes an ester, this makes an ester, and this makes an ester, just like we just talked about in when we were discussing esters. And so what you have here is 3 chains of these fatty acids. And that's how we store energy, okay? So this is something that you probably need to practice. It doesn't really matter what's over here. All that's really happening is you're doing these condensation reactions just like we did before. So you're taking an alcohol right there, and you've got a carboxylic acid, and the two of them come together. They get out water. So yes, there should be plus 3 H2O right here. And that's how you store these things, okay? So fats and oils are mainly triacylglycerides or triglycerides. Since saturated carbon chains have a higher melting point, just like we talked about in the last video, there are more of these in fats. So things like animal fat. Notice that when you get a good steak, it has large amounts of fat on it, right? And when you go to heat that up, you have to heat it up to a high temperature, and still it doesn't all go away. If you did that with an oil, because it's more unsaturated and smaller typically, that would be, liquid a long time before fats would, from like animal fats and stuff. Oils tend to have a much more unsaturated carbon chains, and that's the reason why they're more liquid at room temperature. Okay, so as I was saying on the last video, not to freak you out because it's hard to see one thing at a time here, you can take something like an unsaturated fat, or yeah, that's what that would be, and you can do hydrogenation with it. And these are very controlled reactions, so you control exactly how much of the hydrogen you have going in, and you can get rid of these double bonds to make them more saturated. And that's how we end up getting the solid vegetable oils that you'll see in margarines. So here's something cool to do. Go check out your refrigerator. Go see if you can find something that says vegetable oil spread or made from vegetable oil or something like that, and it's probably just margarine, okay? Now the same way that we can make a fat by removing alcohol, we can actually break this apart, which is great. That gives us energy, right? That's the energy release. Now instead of using H+, like we did before, right, when we were doing esters to carboxylic acids, we now use enzymes. Enzymes are specially geared towards one type of reaction and helping it speed up. right? It's like the catalyst in the body. So this particular type is called lipase because it's a lipid, and ase you'll find at the end of many different types of enzyme words, right? And when you have these, it's the reverse of dehydration. Basically, you just end up getting that 3-carbon alcohol back where you have 3 alcohols and 3 carboxylic acid. So you can actually pull those apart. And then finally, we know that we can do something called saponification. Now, saponification is super duper important. Why? Because this is making soap. Soap is so very important for us, especially right now amid the COVID outbreak, right? So let's talk about what soaps are and how to make them and all that good stuff. Just the same way, excuse me, we could take esters and with NaOH and heat, I'm so sorry, my puppies are in the background, and make these long chains. Remember, this is really sort of a 2-step process. I'll show you this in just a minute. But here we have this OH. This OH breaking apart from this ester, and we have a polar head and we have a long non-polar tail. So here again, we have this OH, and it's the same thing here. So nothing's really changing in any of these. All that's happening is we're taking this ester and we're putting water back in. So another way to do it would be to say adding water here. So let me show you what this reaction looks like. Kylie. Sorry, that's my Kylie. Okay, so we have I'm going to simplify this and just say R, because that's really all we're looking at. If you want to think of this in 2 steps, it might make more sense. So first, if we add H2O, and normally it would be an acid, but we're going to do a base this time. Let's do this in 2 steps. We can say that we have OH, OH, and OH. And remember, it's going to make carboxylic acids. I hope you all can ignore this in the background. She thinks she sees a squirrel, and that's what happens. Okay, and then what we do is we add in and take into account the fact that we have an NaOH. Now, we have plenty of NaOH, and remember, the NaOH is a strong base, so that's Na plus NOH minus, and this is what does the work. So he's a strong base, he's trying to make water molecules. So he's going to say, hey, you're an acid over here, I want to grab your hydrogen, and that's what ends up making that. This stays the same, but that's what ends up making the negative charge here in all 3 cases. So having 3 of them is really like we did before with the esters. It's just you're doing more of it, okay? Now, how does this work? Why does it work? Why is it so cool? When it comes to soaps, it's similar to a fatty acid, but it's even more polar at the beginning because this guy is like super polar head. And this over here is like non-polar, right? So let's say that you have a little bit of oil on your clothing, grease, whatever it may be, and you try to go to wash this oil off, or it can be your dinner plate, whatever it may be, and you're trying to get that off of whatever surface, that oily stuff off of whatever surface, right? Then what happens when you have large amounts of these types of molecules is this is nonpolar. And that's going to attract all these nonpolar chains. So they start to surround it. And I'm not being specific with the number of carbons here. I am just drawing some stuff for you all. Okay, see how they're surrounding this stuff? And it can be even more than what I'm drawing, but for clarity, I'm just going to leave it like that. So you see how all this nonpolar stuff surrounds that oil? Well, outside this like little first ring of nonpolar stuff, what's on the outside? All these things with negative charges, right? So those start to attract water. Why? Because like dissolves like, and they kind of get attracted there because they're both very polar. Okay? And so what happens is, as you start to rinse off your dishes, or as you start to rinse off your clothing, that water carries this whole thing and just takes it away. So it literally lifts the oil off of whatever you have. And if you're wondering how they started making soap so long ago, well, they used oils and fats, and instead of using NaOH, they would like burn ash and process that a little bit, and that basically ends up being some strong base. Now, don't try that at home. Don't, you end up hurting things, but that is something that is part of our history. Okay, cool. Thank you all. Have a good day.